Hi guys, welcome back to Data Every Day. Today we're looking at a dataset of concrete images and trying to detect surface cracks in the images. We're going to use TensorFlow convolutional neural networks to accomplish this. So we have two folders. One is positively labeled images with cracks in them, and one is negatively labeled images with no cracks. And we're going to see if TensorFlow if a neural network can determine the difference between these images. So let's hop into the notebook. I'm importing NumPy and pandas for working with the data, and then these three here for visualization. That's pyplot, Seaborn, and Plotly Express. And then these are for preprocessing. We're using the path object from pathlib and the train test split function from sklearn. And we will get our model up and running with TensorFlow and then evaluate the performance with the confusion matrix and classification report from sklearn. And we'll go ahead and import all of that. And for this, we're going to use image data generator, which is a class from TensorFlow with actually Keras preprocessing. And it allows us to load in images a few at a time so as not to clog up the memory. So what it'll do is load in the images, train on them, and then recycle the memory so that we can avoid just accumulating an enormous amount of unused memory. And we can get the there's a few ways to use the image data generator. One is to flow the images from the directory. There's actually the function flow from directory, which will do that. And that's nice, especially if your directories are made in such a way that you already have a nice train and test set available. However, we don't have a train and test set for us here, and that can complicate things. So we're going to use a different method called flow from data frame, which is basically we load in the file paths to the files into a data frame along with the labels, and then we pass in that data frame to the generator, and it will flow in the images through those file paths. So if we're going to do that, we need to get the directory names for the positive class and the negative class. So we can call this, I guess I'll call it positive dir for directory and negative dir. And the positive is coming from, well, we can just copy the file path to this folder. So if I paste this in and remove the image there, we can get this file path, and I want to make this into a path object. So the path object is very useful. It has a lot of nice built-in functions that we can use to sort of grab all the images however we like. And I'm going to do the same thing here for the negative dir, except change this to negative. So we have our directories, and now let's create the data frames. So I'm going to create a small function called generate data frame, generate df. That's going to take in a directory, I'll call it image dir, and a label that goes along with that directory. So first thing we want to do is get all the file paths. So because we've made it into a path object, let's take positive dir for example. Because this is a path object, we can actually use the .glob function to use glob expressions to find certain patterns in the folder. So for example, let's say I want to get all image file paths ending in .jpeg. We can just do star.jpeg and that will return the generator object. Let's just turn it into a list so we can see all those file paths. And we can see now we have all the JPEG file paths in here. Now if we wanted to get just a certain part of the path, there's plenty of ways to do this. For example, we could map a function to this list. Maybe we wanted to get just the file names and disregard the path. In such a case, well actually for that we may need to import os.path, but we could then use map x, which would be a given one of these paths, to os.path.split x, and then do sub1 to get, sorry, let me turn this back into a list. If we did sub1, we'd just get the file name. If we did sub0, we'd get the prefix leading up to the file name, so the folder that it's in. And so this split function splits, I think if we don't include a subscript, you can see it splits the prefix and the file name apart. And that's just one of the many nice things we can do with this path object. So I'm not really going to do this. I just really want the file paths essentially. So let's just grab this thing and take a look at that. So I want to sort of store this in a pandas series, and then I want to attach some label values to it. So I'm going to create this file paths series using pd.series, and it's just going to take in this thing essentially. However, instead of positive dir, we're going to do this for any image dir that we specify. And I do want to give this series a name, so let's call it file path. And I think that should be good. Last thing though, I do want to turn the series into a string series, because the data type is going to be path, which is going to give us some problems when we use flow from data frame. So we're going to do .asType string. Alright, and now we want to make a series of labels to go along with these file paths. And since we're passing in a whole folder that we already know the labels for, the labels are just going to be given by whatever we pass in as the label here. So that will be another series, and the value for this series is going to be given by label. The name of the series will be label, and the index, it's important to specify the index so that it's the same length as file paths. So the index will be filepaths.index. Alright, and then all we have to do is concatenate these two series together and return it as a data frame. So I'll call it df, that will be pandas.concat. On the left we'll have file paths, and on the right we'll have labels. And so we're doing this along axis 1, which means side by side, and then we will return df. So if we run this function with, let's say we pass in positive dir, and the label, let's say we specify it as 1. You can see it has all the file paths to our positive files. You can see they're all in the positive folder, and our labels are all 1. Now, if we're using flow from data frame, TensorFlow actually requires that we pass these in as strings. So I'm going to call it maybe positive, like this, and that will be good. Now we can do exactly the same thing for the negative set. Just change this to negative, and change this to negative dir. And there we go. We now have everything in the negative folder, and the label is negative. So now let's concatenate these two data frames together on top of each other. So let's grab this and grab this, and we'll call this one positive df, and this one will be negative df. And then once we have these two data frames, we will create an all df, which is both of them, with pandas.concat, positive df, negative df. And this time we're concatenating along axis 0, which means on top of each other. Now, once we do this, you'll notice that it has been done, but one thing, the indices are wrong, because it goes up to 20,000 and then starts over again, since we did just concatenate two data frames that already had their own indices. So we have 40,000 rows, but only 20,000 at the top of the index. And the other problem is that all the positives are on top and all the negatives are on bottom. So we are going to shuffle it later, but I do want to shuffle it now just so that we have a nice data frame to start with. So after we concatenate them together, I'm going to use the sample function to sample 100% of the data, which is the same as shuffling, right? And we'll include a random state so that we can reproduce the result of this. Now if we run this, you can see they're all shuffled around, but the last thing to do is change these indices to be correct again. So we'll do .reset index and include drop equals true to prevent the old indices from becoming a new column. And there we go. Now the indices are correct, the labels are shuffled, and we're ready to proceed. So now that we have this, we can do our train test split. And like I said, the reason we're really doing this whole data frame thing is so that we can manipulate the sets of the data, give ourselves a proper test set without having to go in and change the file directory structure. So we'll use the train test split function from sklearn, and this is going to give us back train df and test df. So essentially we're going to split all df, and we're going to get back two sets of the data. Now for the purposes of the video, I'm not actually going to use all of the data. There's no doubt that if we did, we would get a better model, but because it would just slow down the video quite a bit to use all 40,000 images, I'm just going to use a subset of 6,000 images to train on. So over here I'm going to sample only 6,000 of the images just so that we can speed up the training a little, and include a random state so that we can always get the same ones. Okay, then we specify a train size. 70% of the data will go to the train set, the other 30% will be used for the test set. Shuffle equals true. So this is why we didn't really have to shuffle it up here, but I still like to, so that we have sort of a nice starting place. And then we'll include a random state as well, because anytime we have randomness like a shuffle or something, we do want to include a random state so that we can reproduce it. Alright, and we run this. We now have two sets of the data frame. Train df should be 70% of it, and test df should be the other 30%. Alright, so now we're ready to load in the image data. I'll say loading image data. Alright. So we're going to create two generator objects. I'm going to call it trainGen and testGen. And these are both coming from tf.keras.preprocessing.image data generator. And like I said, this is going to help us deal with the memory issues of training on large sets of image data. This will load in the images, train on them, and then recycle the memory for us. So in here you can specify any sort of data augmentation, image augmentation you want, transformations to apply to the image. I'm not going to do any, I mean, you absolutely could, there's no reason you don't have to, but just to save on time and to simplify the video, I'm not going to include data augmentation right now. But I am going to rescale it because we want to make sure that the pixel values of the actual image data are coming in as values between 0 and 1. And so the standard encoding for pixel values is on an RGB scale between 0 and 255, where 255 is the maximum color intensity and 0 is the lowest color intensity for each of the three channels, since we are using RGB images. So by dividing by the maximum value, or in other words multiplying by 1 over 255, we're essentially scaling all the pixel values down into a range of between 0 and 1. We're also going to include a validation split. So we're going to, we do have the capability of splitting one of these train sets, but the reason we have to use flow from data frame is because we can't split twice. We could only split once, so for a given directory. So I'm going to split the train set into train and validation, and we need a separate generator for the test set. So over here is our test generator. This one we just include rescale as well, but we do not include a validation split. So there are our generators, and now we're going to actually flow from the data frames. So I'll call it train data and test data, and we also have val data. So both train data and test data are coming from trainGen. Test data, train data and val data are coming from trainGen. Test data is coming from testGen. So we're using the flow from data frame function, and we're coming from the same directory, which is train df. Same data frame. So here's the data frame that we're coming from. Both of these data are coming from the same data frame, but the subset is different in each one. So on the top we have training, on the bottom we're going to have validation. So because we specified a validation split, when we pull from TrainGen, if we specify training, we'll get the 80% that's reserved for training, and if we specify validation, we'll get the 20% that's reserved for validation. Now for TestGen, we don't need to specify a subset because we did not include a validation split over here. So we're actually just taking from testdf. Alright, now we do want to include a few more properties here. So we want to specify which column in our data frame is being used as the file paths and which column is being used as the labels. So our X column, that's the file path column, is given by file path, and the Y column is given by label. And that just corresponds to the two names of these series up here, or the columns. Then we specify a target size. So this can be anything we want. This function will nicely resize the images to however we please. These are originally coming in as 227 by 227 images, but we're going to rescale to 120 by 120 just to save on some time and memory. And then we specify a color mode, and this can be RGB. Actually, it has to be RGB since there are 3 color channels coming in. And a class mode. So class mode here is binary because we only have 2 classes, positive and negative. Then we'll specify a batch size. So what do we want to batch the image data into? We'll do a batch size of 32, which is fairly standard. And shuffle equals true. So we'll do another shuffle, even though we've shuffled it like 3 times by now. I just still want to shuffle it. And because we are shuffling, we'll include a seed, which is the same as a random state like I did before. I'll do this as 42, because I feel like it. And we're going to copy this over and do the same thing for validation data. Let me just grab this and I'll overwrite this, but I have to change the subset back to validation. Alright, and I guess we'll do the same thing for testdf. This time we don't have a subset. This time we're flowing from testdf. Everything else is the same, except I have to make sure that shuffle is false here. We don't want to shuffle our test data, or we're going to run into some problems when we're evaluating the model. We want to maintain the order of the test examples so that we can compare them to the labels at the end. Alright, so this looks good. We'll now flow through the data frames, and the function's now going through and finding all the images. It's going to count them up as well. So here we go. It found 3,360 validated images belonging to 2 classes. So this is the train set, this is the validation set, and this is the test set. And you'll see these are, if we add these all together, it will add up to 6,000, which was the number of examples we took to sample. Alright, and now we have our image data loaded in. Let's start training. So we're going to do a pretty standard convolutional neural network today. 2 convolutional layers with max pooling in between them. And let's get started. So the input layer is just going to be tf.keras.input. The shape here, it is going to be a 120 by 120 by 3 image. This comes from where we specified the target size up here. And the 3 is the RGB color channels coming in. Then we're going to have our first convolutional layer, conv2d. And the convolutional layers, the purpose of them is to extract features from the images. So it basically, it's almost like, because we pass in just an array of pixels, the convolutional layers sort of like looks at areas in the image and sort of extracts new features out of the image that can be used for classification at the end. So this isn't the classification part of the model yet. We specify a number of filters, which is essentially how many times are we looking at the image with different weight values. I'll start with 16. Then a kernel size, which is the size of the window that's sliding across the image. We can do 3 by 3, which is default. And we'll include a ReLU activation after after the convolution is complete. And then we'll have a max pool layer. So maxpool2d. This will take the convolution output and just reduce the dimension of it. Basically also apply a kernel across, which is given by pool size. We'll do 2 by 2, which is default. So it'll take a 2 by 2 window across, and it will just take the max of whatever is in the 2 by 2 window. So it'll slide across and just output the maximum from each window, and therefore reducing the size of the output. Then we'll have our second, we have to pass in inputs here, and pass in x here. Then we can just copy this over and do a second convolutional round. This time we pass in x. And the only thing I'm going to change from this is up the filters to 32. So these you could consider as the first features that the model grabs from the image. So we're just taking 16 of them, and then we're looking at those features and taking out 32. So one intuition you could have is that these are the low-level features and these are the higher-level features. Maybe these are edges or lines in the image, and maybe these are the actual crack sizes themselves, crack patterns themselves, which are a combination of lines and edges. But that's not necessarily what's happening. It's just one way you can think about it. Okay, and so again, we've pooled it down, and then we're going to use an average pooling layer. So that's actually a global average pooling. So you could either flatten the image or do a global average pooling. And what this basically does, at the end, we have a 2 by 2 output, because the convolutional layers and the max pooling layers do output a two-dimensional output. And before we perform the classification, we need to reduce it down to one dimension. So one way we could do this is by flattening the layer with a flattened layer. Just take the rows and stack them like this, so that you just have one long output, single vector output. But the other way, another way, is to use a global average pooling, which basically just takes the average down the axis 0. So it averages across all rows. And then we're going to pass x through here and get our outputs. So at this point we do have a vector, and we can now do classification with a sort of dense way, a dense layer classification like you normally would. And so I have to point out, normally in a binary classification problem, if we were specifying standard labels, we would output one activation or one output with a sigmoid activation. This would represent the probability estimate for the positive class. However, when we're using flow from data frame, let's take a look at this. Look at our trained data, for example. If we type .next, we can get the next batch, and that will give us some data from it. And then when we do sub 0, we'll get the image data, and if we do sub 1, we'll get the label data. Okay, so it's actually interesting. This is outputting it as proper zeros and ones. Earlier I was getting a problem with this, so I'm going to try it with the sigmoid, see how this goes. And passing in x here. Okay, so this is the full model. Basically, this whole part of it is dealing with feature extraction, looking at the image and taking out features from it that it can use for this part, which is the classification aspect. Actually try to make a prediction based on the features it found. And then model.compile. Actually, first we have to create the model. Model equals tf.keras.model. We specify the inputs as inputs and the outputs as outputs. And then we'll compile the model. So we'll use an atom optimizer. The loss function, since we are doing a one-valued sigmoid output, should be binary cross entropy. And then metrics, we'll just use accuracy. Alright, let's print out a summary of the model. Alright, so here you can see we take in a 120 by 120 by 3 image. The convolutional output is 118 by 118 by 16. We lost two values here, it went from 120 to 118 because the window can't slide out out past the image bounds. So we have a 3x3 kernel, which is the window, and there's one pixel on either side that gets lost. So that's why we have the 118. The 16 comes from how many times are we looking across it. So we go across it 16 times, each time with a different set of weights, and then we get 16 different outputs. So this then gets pooled down. Just the 16 stays the same, but the size of the output gets pooled down via max pooling. Then we have another convolution across this max pooled output. We also lose 2 pixels here due to the window size. And we do this 32 times, so we now have 32 outputs. This gets pulled down again with max pooling, and then finally we average all the way down across. So you can see we're actually averaging across 2 dimensions, so that we get a final set of 32 outputs. So we're averaging down across the x pixels and the y pixels, and we finally just get a single vector of the represented by the depth, or the features that the convolutional network found. Okay, so after we have that, it is just a single vector. We then just do a proper classification with a dense layer down to 1 value, which will be a probability estimate of the positive class. And now let's try to train. So I'm going to store the history of the model's fit in history, and we'll use model.fit to do that. Now we're fitting on the train data, so we can just pass in the train data as it is, as a generator. And then validation data is just given by val data, which is taken from the same df, but this time with the validation subset. And then the epochs we'll train for 100 epochs and use an early stopping callback, which here is tf.keras.callbacks.early stopping. This allows us to monitor a value, let's say val loss, validation loss, and when it notices the validation loss is stopped improving for a certain number of epochs given by patience, let's say 3, it will stop the training and restore the weights from the best epoch with restore best weights equals true. And that allows us, we don't have to manually adjust the epochs, we can just train for a large number and then it will automatically stop when the model stops improving. Notice we don't have to specify a batch size here because we did specify it up here. Alright, and let's give this a try. Alright, I would actually, okay, I could enable GPU acceleration to speed this up, because for image classification tasks, GPU acceleration can be very beneficial. Yeah, I guess I'll do that. Okay, so let's go here, accelerator, GPU. I just have to close out of my other notebook and then click it here. Alright, so that will actually restart the kernel, and I will resume the video when we get back to this point. Alright, so I finished training on the GPU, and you can see that we're doing quite well with a validation accuracy of around 98% towards the end. Now I'm just going to quickly use Plotly to get a graph of the training loss over time. So we'll create a Plotly figure with fig equals px.line to get a line chart. And we're going to draw values from history.history, which is the dictionary containing the list of loss and accuracy values over time. And on the y-axis, I want to draw loss and val loss from history.history. Then our labels here, the index will be, which is the index of the dictionary, will be epoch, and the value will be a loss. And that will just be the axis labels. Then for title will just be training and validation loss over time. Alright, then fig.show, and we can take a look. So here it is. You can see that as we went on, our model just got better and better. The training loss is constantly decreasing. However, the validation loss reached a point where it finished decreasing and then started going up. Now, Maybe if we had specified the patience value to be higher on our early stopping, we could have trained for a little longer, I'm not sure. But this looks like this was the lowest loss it had, and then it went up for like 3 epochs, at which point it said stop and return the weights from the best epoch. So you can see our model does seem to be converging nicely, and our accuracy values in the validation set do seem to be indicative of that. So let's get some results now. So I want to plot the results of this model. I want to take a look at a confusion matrix, and I'll use a classification report from sklearn to sort of analyze that more nicely. So I'll create a function called evaluate model. This will take in a model and the test data set, which is really a generator, but we're passing in from above. And we'll start off by getting the results of the model with model.evaluate. So we pass in test data, and I'll specify verbose equals 0 so we don't see the loading bar. And then we'll get the loss from results sub 0 and the accuracy from results sub 1. Yeah, so this returns 2 values. It'll also return whatever metrics you specify, but we only specified one metric as accuracy. So we get the loss from the first element and the accuracy from the second. And we'll print those out. So test loss, we'll display that to 5 decimal places and format this with loss. And then we'll do the accuracy, which we will display to 2 decimal places with a percent sign, and format that with ACK, but times 100 since we want to see it as a percentage. So right now this will just give us the loss and accuracy. Let's indent this for the test set. So now I also want a confusion matrix. And the way this works, if we're using the confusion matrix function from sklearn, it's going to take in a set of true label values and then a set of predicted values to compare. And we can get the true label values from testData.labels. This will be the true labels as integers. 0 is the negative class, 1 is the positive class. And we get the predicted values from model.predict on the test data. So if we actually run this, you'll see that it should return a bunch of probability values instead of just zeros and ones. And that's because we specified the model to return a single output with a sigmoid activation. So these are actually, this will return the actual outputs of the model for every test example. Just give it a second. Not sure why it's taking so long. Alright, it finished. So here are the actual probability values. So if this is low, it's actually, the threshold is at 0.5. So if it's less than 0.5, other way of saying that is if we have less than 50% confidence that it's a positive value, positive label, then we'll classify as negative. And if it's greater than 0.5, the closer to 1 it is, we'll classify it as positive. So you can see maybe these are matching up. The 0 goes to the 0, this goes to 0, and this is quite high, so it goes to 1. But we don't want it like this. We want to sort of turn it into this. So the way we could do this is take this NumPy array and ask, is it greater than or equal to 0.5? And this will return a true or a false for every example, which we can then do .asType numpy.int to change the trues and falses into ones and zeros. Actually, oh yeah, okay. So that works. We now have zeros and ones. You will notice that this is two-dimensional, whereas this is one-dimensional. So if we want to avoid that, we can use numpy.squeeze on it to squeeze out that extra dimension, and then we should get the same sort of dimensional data. Alright, so let's use this in our function. So we'll call this ypred for predicted y values, and I just have to, no, that's good. It's taking in test data now and then getting the predictions. And then we'll get our confusion matrix and store it in CM by passing in the testData.labels, which are the actual values that we got. and then our ypred, which is our predicted values. Then we'll get a classification report, which also takes in the same format, so we'll pass that in, but I want to specify the target names here, which is the label names. So negative and positive, and that will just make it easier to understand what we're looking at. Now, last thing I want to do is plot the confusion matrix with Seaborn and then print out the classification report. So I'll create a new pyplot figure with a figure size of 6 by 6, and then use Seaborn's heat map to display the confusion matrix. I'm going to turn on annotations. I'm going to use format equals G to prevent the classification counts coming up as scientific notation, so I do want to see them as integers. Set the minimum color value to 0. We'll give it a color map as well. Blues looks nice. And then turn off the color bar because it's sort of useless in this case. Then I'll give it some tick marks. So we have to specify the ticks, which is the spacing of the ticks, and we can use a NumPy A range for this to just get two values, which will be 0 and 1. But those tick locations actually specify the corners of each box, so I want to shift them over by 0.5 to get the ticks into the middle of the box. And then the labels is going to be given by this list right here. And I'll do exactly the same thing for the Y ticks. Alright, then on the X label is going to be predicted. The Y label is going to be actual. And the title is going to be confusion matrix. Then we'll show it. And last thing I want to do is print out the classification report. So I'll just include a bunch of hyphens to make it look nice, and pass in CLR at the end. Alright, so let's run this with evaluate model and pass in our model and our test data. So this should print out the loss, the accuracy, plot the confusion matrix, and then show us the classification report. And here it is. So we did quite well in the test set, 97% accuracy. The confusion matrix is showing us we have very few misclassifications compared to correct classifications. So here are the correctly predicted negative values. Over here are the correctly predicted positive values. Here are negative values that we predicted as positive, and here are positive values that we predicted as negative. So you can see we have some metrics about this confusion matrix here. For a given class, let's look at the negative class first. We have a precision of 0.96. This just means out of all of our negative predictions, which are these two boxes here, we got 96% of them correct. So the other 4% is right here. So that's really good. I mean, all of these are good. I'm just looking at each of them. The recall for the negative class is saying out of all the actual negative examples, we got 98% of them correct. So the other 2% is right here. And then on the other hand, the positive class, our precision is given by this comparison, which is 98%, and the recall is given by this, which is 96%. And then the F1 score is a combination of precision and recall. It's calculated by 2 times precision times recall all over precision plus recall, which has the effect of being a 1 when both precision and recall are 1, and a 0 when either precision or recall is 0. So it's a nice way to get a single value metric for evaluating the performance of a model that's more considerate of the performance between classes. Accuracy is not a good metric when especially if you're dealing with imbalanced class distribution. F1 score is much better to use. Alright, and that will sum up today's video. So thank you so much for watching. I hope you enjoyed. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.